Welcome to Breadboarding. In the previous video, we got the Breadboard PC with the power on self test port working, and this is some of the logic analyzer output where we showed the test codes that we sent out starting at FF255 going all the way down to 0. This is video 9 of the Breadboard PC 8088 version 2. In this video, we're going to be adding the interrupt controllers, setting up a BIOS, and also installing the real-time clock. So in our high-level plan, the previous step we did was the power on self-test port and port B, the timer and the speaker. So we were able to get the timer to produce beep codes coming out of the speaker. And once we've done the interrupt controller, real-time clock and BIOS, there's only a few more things we need to do to then be able to boot MS-DOS. So setting up a keyboard, having a video card, and the floppy disk controller. In the previous video, we looked at what makes a microcomputer IBM PC compatible. The things in green we kind of already taken care of. The things in pink or purple are what we're going to be looking at during this video. So adding a BIOS which is compatible with the IBM PC software interrupts. Adding the interrupt controller needed for the keyboard timer. We'll also be adding the real-time clock. So this has CMOS back memory, so the configuration of the PC will be stored in memory rather than in dip switches. And it will also mean that we don't have to keep on typing in the date and time every time we boot up MS-DOS. This is a chart that we had in the first video in the series. It looked at our PCXT hybrid that we're building and where the various parts came from. Some of these from the original PC and PCXT, but the ones we were looking at today, the real-time clock and dual interrupt controllers, this gives us extra interrupts to allow us to be able to do the mouse and the real-time clock. So these came from the PCAT, and then we're going to be adding these other items from later series computers in future videos. So what is a BIOS? Well, BIOS stands for Basic Input-Output System, and really the first micro BIOSes were developed by Gary Kildale around 1975 for one of the early micro operating systems, CP/M. And it isolates the operating system like CP/M or MS-DOS from the hardware differences, and this allowed Gary Kildale and Digital Research to be able to convert CP/M to run on different manufacturer hardware platforms quite quickly and easily. So BIOS is generically known as firmware, and this tends to be stored in read-only memory, EPROM, EEPROM, electrically erasable programmable read-only memory, or in more modern machines, flash memory. Now the IBM PCXT BIOS supports about 15 software interrupt functions. In order to be PC compatible, then the BIOS needs to support most of these functions. So the Wikipedia article here, which the link is there, shows the majority of these functions. So you'll see that some are relatively straightforward. The interrupt 10 is all the video services, so you can see there's lots of different functions there. Low-level disk services, which can be used for both floppy disk and hard disk. So in order to be PC compatible, then the BIOS needs to provide support for the majority of these things. Not all of them are necessary, but certainly the majority are. And then there are certain other functions that are added with the PCAT, for example, the real-time clock functions, for example, there. Now, the original technical guides that came with the PC, PCXT and PCAT, the technical reference included the source code for it. And this is one of the reasons why the PC, I think, became such a success. Although it's an IBM design, IBM actually published most of the information you needed to be able to reproduce such a device. Clone PCs tended to use the third-party BIOS generally available from Phoenix and Award, and these are sort of things where you'd have the blue setup screen you may be familiar with on some PCs. However, the Compact Portable developed a cleanroom BIOS, so the way how this was done is that the developer never saw the IBM BIOS documentation, and a number of other developers developed a specification from that documentation and gave to the BIOS developer so that there was no chance of them actually copying any of the original BIOS code. Now the BIOS provides the power on self-test messages, tests all the memory and other devices, and will also provide all the boot failure messages and things if it can't find a valid operating system on the floppy disk, hard disk or other boot devices. Now we'll be using the XI8088 BIOS, which has been written by Sergey Kiselev along with his XI8088 PC designs. And the GitHub URL here will be in the description below the video. If we just have a quick look at that. So the Sergey site has a lot of resources, a lot of repositories here, lots of designs of various ISA bus compatible cards, so network cards, floppy disk controllers, all these sorts of things. But the BIOS here is really the thing I've been using the most. And there's a lot of documentation here. I'm just going to cover how to build this and what changes at a high level I've made to get this working with the Breadboard PC. So we need to download the BIOS. What I have got is the original files in one folder and the Breadboard PC current version ones in another, and I'll go through and compare those in a few minutes. We need to create a Breadboard PC configuration and its own configuration options. We've needed to shuffle the code around a bit, so we've actually moved the BIOS up a bit. We've moved it up 4K from the initial starting point, which was the F8000, which is the bottom of the 32K up from at the top of address space. And that will allow us to put the XT-IDE BIOS for accessing the hard disk in there in future videos. We've also configured it to include the nanocomp monitor, currently on version 7, and this is configured to actually run on reset and is located at FC000. The nanocomp monitor B key will actually boot the BIOS, and as far as the BIOS is concerned, it will have just started after reset. There's some changes needed to make around the video controller configuration to work with VGA output frequencies, but we'll be covering that when we do the CGA video controller. There were some areas we needed to comment out some of the set lock macros which fix certain functions and things at a hard-coded address so that software that actually called the BIOS functions directly rather than through a software interrupt would still work. Now that's less of an issue for us because we're not really going to be trying to maintain that level of compatibility. We also modified the floppy disk functions to remove DMA and to use programmed I/O, but we'll be covering that when we come to the floppy disk controller. But I have had to comment out the PS2 keyboard initialization because we don't have a PS2 keyboard controller at the moment, and at the moment the code does a CPU halt on failure of initializing that, so that needed to be commented out for us to be able to use the BIOS. So let's have a look at the changes necessary to get the BIOS working on the Breadboard PC. We're only showing the things which are different where I've actually made the change. Now, the main file with all the stuff in is the BIOS ASM. I'm just going to go through, we'll cover some of the main changes here. There's a few typos and things I've corrected along the way. And you'll see here that there's a number of areas where we're outputting a code to the power on self-test register. And in this particular case, I've just added a comment around the DMA. The port 80 also happens to be the DMA page register for DMA 0. Now, there are a few corrections as well. There were some problems I had in the early stages. There needed to be extra if-def end ifs around some of the commands that would cause the BIOS to not assemble under certain configurations. Then we've got the nanocomp monitor included. You can see here we're setting the location for that to be C000, and that's the current version 7 of the monitor that we looked at a couple of videos ago. Then there's a few things there to do with the software interrupt vectors that we just need to configure those so that if we want to use the nanocomp monitor for debugging and looking at registers and things like that, then those are necessary to allow the non-maskable interrupt to actually go into the nanocomp monitor. There was a correction there. I think the comment in the original code is every 15 milliseconds. This is actually every 15 microseconds, this clock signal. And you'll see here that's where I've commented out the keyboard controller in it because that does a halt under errors. So this is then some of the code where I've added Breadboard PC specific code to initialize the VGA palette, which is used with the CGA compatible video controller. When doing the mouse, I needed to include a sub-byte because some of the mouse drivers were having trouble working, and we messed around with the various model information coming out of this particular function. And it seemed to be that the Microsoft mouse driver would be happier with certain PS2 models. Also changed some of the flags there for the mouse support. Now this change here is necessary to be able to use the XT-IDE BIOS. So by default, it would only search for additional BIOS ROMs up to F800, but because we were putting the XT-IDE BIOS actually at F800 up to F900, then in fact we needed to extend the scan so it would actually find the XT IDE BIOS. And there are various places where we've changed this set lock. Just means that the code can shuffle up and allows new code to be added in without actually causing problems. Then you'll see that there's quite a lot of entries here where when doing the floppy disk initialization and booting from floppy disks, there's a lot of power on self-test codes that I've added diagnostic information there. Again, we'll cover that in more detail when we do the floppy disk side of things. Again, various diagnostic messages to do with the boot process. You can see here that the reset vector would normally jump to the BIOS cold start, but in fact what we do in this place is we actually jump to the nanocomp monitor, and then the nanocomp monitor will use B to effectively jump to cold start. So this just means that we can do a bit more diagnostic work. So those are the main changes necessary to make to the BIOS itself. And then it's necessary to create a breadboard PC configuration. So we've got a breadboard PC configuration in this config file. And then we've based these different options and things is a superset really of the XI88 and a couple of other options and things there. And I've also changed it to have a one default 1.4 megabyte floppy A drive rather than 2. I won't go through the changes to the floppy controllers just because there's quite a lot of changes there to do with programmed I/O, and we'll cover that when we talk about the floppy disk controller. The message is just some changes to do with changing the ROM scan from F80 to F90. You'll see that a lot of these things have only got changes to set lock, and there's a few other things where, for example, when we're reading the CMOS configuration, then I added some extra power on self-test port messages just so we could read what was coming out of those. The printer PS2 AUX will cover in later times, as will the time and the video will cover at a later point in time. Now, to build the BIOS, we need to go to a command prompt, and there's the make process there. We just type that. You'll see here that where we're padding out the code with this set lock macro is padding out the code so that functions start at a particular address. You can see how many bytes are being added here, and you can see around where the video is, then the number of free bytes is very, very small, whereas further on down we've got sort of 6.5K of space. But when I was first doing this, I needed to change some of the padding here so that it actually work okay. And then we will actually have here, so you can see here, this is the BIOS breadboard PC, and you can see that in fact it's not 32K, it's actually 28K, because the first 4K is reserved for the XT IDE BIOS. So I've already programmed that into the EPROM, so we don't have to worry about doing that. Sometimes I forget to do these sorts of things. So let's go back to the slides and then we'll look at some of the other things. So that really covers what we need to do for the BIOS. So all we need to do when the nanocomp monitor boots up, just type B and it will go into the BIOS. And what we should hopefully be able to hear is there is a little tune. It does an Intel type CPU tune that BIOS does on power up. So we should actually be able to hear that hopefully. So then we're going to be looking at adding the real time clock and the CMOS setup. So the PCAT, which was the 286 version of the PC, introduced a real time clock. So that meant you didn't have to enter the date and time on each DOS reboot. Anyone who's ever used the original PC, it was a real pain to have to keep on typing in the date and time each time. And if you didn't do it, you'd end up with all the date timestamps on your floppy disks would all be based on sort of 1980, which really wasn't very helpful. There's a battery-backed CMOS memory that allowed the configuration to be stored, and it has a checksum as well. So if anything gets corrupted, then you'll get a bad CMOS checksum. And this meant there were no DIP switches. The PC PCXT had various switches on the motherboard that you needed to configure the memory and various other options. There's a BIOS setup utility to maintain those settings. So the PCAT had a diagnostics floppy disk setup option, and the XI8088 has a built-in setup screen, a bit like the Award and Phoenix BIOSes and more modern BIOSes we'd be aware of. And the following slides actually come from PCJS, where it actually has a PCAT, and if you load the PCAT Diagnostics 2, then this is where some of these screenshots have come from. So what you had to do, it wasn't built in, obviously, like pressing F1 or F2 or something like that during power up. You actually had to boot off the diagnostics disk. It would allow you then to run setup, enter the current time, and date, press yes, then would review what the current configuration options are, and you could then actually go in and modify that, the number of disk drives, what the parameters for the fixed disk was, and all those sorts of things. So we'll be looking at that in future videos. At the moment, we're not going to be able to look at the BIOS output messages because at the moment we don't have a video controller. But I'll be looking into that in future videos when we add the CGA card. So the PC80 and the Compact Despro 386 use this particular real-time clock chip. It had a 5 microsecond cycle time, so you needed to access it sort of fairly slowly. Now, modern real-time clock chips are register compatible, and we'll be using the Dallas Semiconductor DS12885, and that's the same one as is used on the XI8088. Now, the CMOS and the clock battery are backed up via a sort of 3-volt button cell, which we'll actually put on the breadboard. Now, the interrupt controller requires an interrupt line to be active high, whereas the output from the real-time clock is for active low. So we do need to invert the interrupt output, and one of the PLDs we looked at last time, the ready wait speaker PLD, includes the invert for the interrupt 8 for the real-time clock. And because this is interrupt 8, it does require the second interrupt controller. We use the IO port range 70 and 71. And one of the things to note on the diagrams, I will show that the chip select was actually an inverted value of the power good that came out the power supply. This was actually to make sure that the real-time clock couldn't be updated until the power supply was in a good stable situation, so you didn't get corruption. So this is the original PC80 circuit diagram, and you'll see here that the power good coming in here goes through these inverters to actually provide the chip enable. So this is how PC80 prevented the configuration of the CMOS here getting corrupted during power up activity. Then this is the Compact Despro 386. Again, quite a complicated circuit here because of the oscillators and the various power input. In fact, the chip we're using does all of this stuff effectively on the chip, so it makes things a lot simpler. And you'll see there that the output for the interrupt there has an invert there to go to IRQ8. And then this is the output from the XI8088 KiCad schematic. So you'll see here that the oscillator is connected directly to the real-time clock chip. There's a battery backup there, and there's also a link there to clear the CMOS. So when the power is off and it's running off the battery, if we ground that input, then it will set all of the internal CMOS configuration except for the date and time will be set to 1s. Now there's 3 inputs here for controlling the reading, writing, and the address enable here. So those 3 lines are already available on our IO decoder PLD that we installed last time. Now, one of the issues that I covered at the end of the first Breadboard PC series was that the real-time clock seems to run fast when the PC's powered on. And when I actually looked at the clock input, so the X1, X2 clock inputs there, when the power is off and it's running off the battery, then the input there is actually quite nice and sine wave-like. However, when the power is on, then there seemed to be a lot of interference from the data bus, and if you see here, the D0 data bus line here is very close to the input pins, and because this was connected directly to the main data bus, then it was never very quiet. Now what we're going to be doing is also plugging in a system bus bidirectional buffer, so it'll actually isolate the system data bus from the main system bus unless one of the chips actually behind it is being addressed. So this should hopefully resolve that. If that doesn't address it, and we'll keep an eye on this when we first start up MS-DOS and see how accurate the clock is, then one of the options we could do if we've got MS-DOS running, we could just bend these 2 pins out of the breadboard and actually solder the crystal directly to them, and then perhaps put some shielding around it should it still be an issue. We're not going to be able to really test that out until we've got the video output from the BIOS and we're able to actually use the keyboard to set up the date and time. We'll look at the configuration for the interrupt controllers on the main KiCad schematic in a minute, but there's just one thing we need to be aware of. This is the diagram from the original PCXT. This only had 1 interrupt controller, But there was a particular issue that I came across in the first series of the Breadboard PC, in that the interrupt acknowledge output from the CPU or the bus controller, in fact here, in our case, we're actually getting that directly out of the CPU. It did require a pull-up resistor here. You can see there's a pull-up resistor there, and I did need to add that in, so I have made sure I've added that into our KiCad schematic. And if we look at the XI8088 schematic, then the interrupt controllers down here. So this is actually using the PCAT style, where it had 2 interrupt controllers, and we'll have a look at the configuration there in a minute. In the KiCad diagram, you'll see here the 2 INTA values there, and there is a pull-up resistor for INTA there as well. So the XI88 included this. We just need to make sure we include that on the KiCad diagram. So let's take a look at the KiCad diagram and see what we're actually going to be adding during this video. So last time we added the speaker, timer, the I/O decoder, the power on self-test port, the port B read and write, and in this video what we're going to be doing is adding the real-time clock here with the crystal and the backup battery and our CMOS clear jumper setting there. We're also going to be adding the system data bus buffer here, so all of the data bus on this side of the circuit, so you'll see the interrupt controllers and all these other devices over here are all actually running off this data bus, so it's isolated from the main data bus here. And the problem I was talking about with the real-time clock being running fast is that this value here will only be connected to the main data bus when the CPU is wanting to talk to one of these devices here. So really it should be a lot quieter, and hopefully this will avoid the interference. The occasional times we do access it, I don't think it's going to cause too much trouble, and obviously if it does, then we've got that option of perhaps bending the pins there. So this system data bus buffer is a bidirectional buffer 74LS or ALS 245, and this is driven by the sysbuffer chip enable. If you see here, the sysbuffer chip enable comes out of here, and basically what this does is this will enable this if any of these outputs here on this side over here are being accessed either read or write, then this will be enabled. And you'll also see that the direction, so by default the direction going from A to B is when the CPU is writing data to the chips over here, and it's B to A when it's reading. So this is data transmit receive, and if we look at this signal here, this actually is also the same one that actually drives this main data bus buffer here. You'll see here that DT/R, and we can see that DT/R actually comes straight out of our 8088 CPU, and it's also available actually on the bus through this buffer here. So all we should need to do is to hook that into there and hook the sysbuf CE, and then this data bus buffer should be okay. And previously I think we'd wired in our main data bus into one of these chips over here because it wouldn't quite reach the timer. What we're going to be doing is changing that cable to here, and then this cable will probably go over to the timer, and that will hopefully sort ourselves out. Then we're also going to be installing the interrupt controllers. So there's 2 interrupt controllers, number 1 and number 2. They're configured very similarly. You'll just notice that we've got the programmable interrupt controller 1 and programmable interrupt controller 2. We've got the data bus, I/O read, I/O write. These cascade 0, 1 and 2, this is related to how the interrupts can cascade from one controller to the other to give us our sort of 0 to 15 interrupts. There's a pull-up on this one. This is in the legacy terminology of master-slave. So the master is controller 1 and the slave is configured by SP being 0. You can see here that we've got interrupt 8 up to 15. But when an interrupt occurs from this controller, what in actual fact happens is the interrupt output here is going into IRQ2 on the first interrupt controller. So in fact, IRQ2 is in fact kind of like the chained interrupt for the other controller. And you also see that there's this INTA Acknowledge signal that comes in. Again, this is coming from the CPU itself. And what happens is when there's an interrupt flag by the interrupt controller, the CPU will then send out two low signals on here. And on the second low signal, what the interrupt controller will do is actually provide a byte value, which is effectively the interrupt vector for the interrupt that has been triggered. And that will actually be an offset to the interrupt vectors in the first sort of 1K of RAM on the PC. And when we're testing this, what we'll be looking at is once we've got the BIOS running, then there is a system timer that runs at I think 18 Hertz for 18 times a second. And each time the system timer runs, then what will happen on IRQ0 here will trigger this interrupt. And what we should be able to see is 18 times a second, we should be able to see the interrupt being triggered, the int being raised by this, and then the INTA coming back from the CPU. And we should be able to see the appropriate byte being put on the data bus here by the interrupt controller. You might just need to make sure that the rules here for the sys data bus buffer are actually also enabled such that when INTA is low, then we also need this buffer to be able to actually allow the data to come out. So that might be something that we haven't actually included at this point in time, so I might need to go and check that. The real-time clock is going to be plugged into the PLD down here that we did last time, and then we've got the read and the write signals coming out here. We also need to hook in the reset, but pretty much other than this sort of inverted interrupt, we've got pretty much everything that we need set up for this, so it should just be a matter of wiring this in. So let's take a look at the breadboards and actually see where we're going to be plugging everything in. So this is the board we were working on in the last video, and the data bus buffer is actually coming in on this wire. This was because it wouldn't quite reach up to this one over here, so this is just going to come out of here and go in here, and then we'll be hooking this one over here to here, and it will then go to these other ones there. So real-time clock chip, so I've got the chip label there ready to stick on the chip. And we'll also be putting the backup battery in here as well. This is the 74LS or ALS 245 bidirectional buffer and our two 82C59A Intersil interrupt controllers. These are modern chips, so these were bought from Mauser in the last couple of months. These are still available, unlike in the previous video series I was trying to use original 1980s parts where possible. These are still available and they should be a little bit faster and shouldn't be susceptible to problems with clock speed. So what I'm going to do now is to put the labels on the chips, plug the chips in, and we'll wire everything up, going back to the schematic as we go, and then when we come back hopefully we'll be in a position to power this on and see if we can get anything coming out of the power on self-test codes from the logic analyzer here that's connected to the post port down here. And we should also be able to hear some of the sort of beep tones as the BIOS actually powers up. So just going to put in the backup battery connector in there, put in the real-time clock. I'm going to move that power connector over the other side, just wiring in the ground and 5 volts lines and wire in the backup battery there. And the jumper is for the clearing the CMOS memory, so just checking those off there. Now we're going to be doing the Motorola Intel by to the ground and the crystal. It's in Intel mode and we've got the 32 kilohertz crystal. Just going to wire in the data bus there, and then we're going to put in the system data bus buffer and just wire in the various data lines there. Just need to put in the power rails for that and the system buffer enable from our I/O decoder, and then the DTR from the main bus. Okay, so now we just need to do the write enable, read enable, and the address enable for the real-time clock plus the reset. Plus we're going to be wiring in the interrupt lines That's the reset just going into one of the other reset lines there. This will now be the read enable, the write enable, and the address strobe as well. That is just the interrupt going up to the PLD there to get inverted, and the tie up to 5 volts there. So now we're going to do the 2 interrupt controllers. We need to do the chip enables first and the IO read and IO write, and then the CAS 0 to CAS 2 at a later point in time. So I'll just put those in, give more holes at the top there. Okay, so we're going to do the power rails first of all, and the tie to ground. So for controller 1, that's tied to 5 volts. Secondary controller is tied to ground. Putting in the power rails and the tie to ground and tie to 5 volts. So now we need to put in the chip enables for the interrupt controller 1 and interrupt controller 2 for the IO read and IO write. So bringing in the chip enables first, then IO read and IO write just on the left hand side there, and we can just bridge those across. So now we need to take the interrupt out of controller 2 and feed that into IRQ2, then also feed in IRQ0 and IRQ8 into the interrupt lines there. So that's IRQ2 and INT, and then we've got the other 2 interrupts there as well. Now we need to feed the interrupt acknowledge over to the PLD there and into the main bus. That is INTA over to the PLD, tie the 2 chips together, and then we're just going to wire the interrupt and the int acknowledge to the main bus there. Now we just need the CAS 0 to CAS 1, so this does the cascade of the interrupt controllers. The 2 can coordinate. We're just going to do the data bus now to hook the data bus into the system buffer there for the 2 interrupt controllers. Just put in the decoupling capacitors as well. Now we just need to put in the A0 line, so this allows us to select between 2 addresses for the... Okay, so we've got everything plugged in. I had forgotten to do the address line, so we just snuck those in at the end there. So I've got some of the logic analyzer signals connected up there, so we'll have a look at that in a minute. But first of all, I did mention about the interrupt acknowledge and whether or not we might need to make some changes, and in fact I did need to make some changes. So this is the original PCXT diagram, and what this shows is that interrupt acknowledge down here, if we just zoom in. So interrupt acknowledge actually goes into some gates here that actually control the direction for the buffer for the X bus data, the XD data. So this is the original PC, so it's definitely something to do with the direction. So we could read the byte that's put on the data bus by the interrupt controllers when the CPU is acknowledging an interrupt. And if you look at on the right hand side here, this is from the XI8088, and in fact the input to the direction on this buffer, the X bus buffer here, you can see that we've actually got the interrupt acknowledge, the IO read, and also in fact the A8 and A9. And what that is because of all of the devices on this, all the IO devices on the X bus here are all actually in the 00 range for the IO range, and that's the same as the signal that we've got for our buffer in the logic that we're doing at the moment. So looks like it is something that we need to worry about. We have added the interrupt acknowledge is now going into a spare pin on our IO port decoder, and what I've done is I've modified the rules here such that the sys buffer chip enable now actually has the necessary logic conditions to include this. This is version 2 of our IO decoder, and you'll see I've added the interrupt acknowledge there. Again, we've got the negative polarity for this. And then all I've needed to do now is to include a condition for our sys buffer chip enable. Now actually includes the interrupt acknowledge as well. The chip labels have been updated and I programmed that, and so that's all installed and working. Now, in order to test this, since we've already configured the BIOS, then this is a slide that I did in the previous series that just showed the sort of order in which things happen in the BIOS startup sequence, certainly with the XI8088 BIOS. Now, I'm not expecting it to go all the way through here, but we should be able to see that the codes that the BIOS gets through will go a certain amount of the way here, and hopefully we'll hear the sort of Intel little tune, the BIOS power up, and that will actually give us an indication that at least the BIOS is operational. So for testing the interrupt controllers, what we're going to do first of all is the first part of the test is going to be the power up sound, because this uses the programmable interval timer. And also what will then happen is that there is a system timer on the PC, which one of the channels for the programmable interval timer is connected to IRQ0, and that generates an interrupt about every 55 milliseconds, about 18 times a second. And that's actually used for a number of things, including updating the system clock when it didn't have a real-time clock. So if we hear the power on noise, the Intel tune, then that indicates that at least the timer is working. And what I'll also do is I'll run the test program that we did in the previous video just to make sure that's working and that we're getting power on self-test codes coming out on the logic analyzer. So then to check that the programmable interrupt controllers are working, we're going to be checking on the IRQ0 system timer interrupt that occurs about every 55 milliseconds. And this was originally used to update the clock information running in DOS before it had a real-time clock in the PCAT. And after each interrupt, what we should get is 2 interrupt acknowledges, and the PIC is then going to need to put the information to do with the interrupt number on the data bus. So the PIC1 interrupt vector that interrupt 0 should have is 08, and that is actually part of the initialization. And our PIC2 has an offset of 70, so all of the higher interrupts actually start at 70. So what should happen is when we get IRQ0, we should actually see 08 being written to the data bus on the second interrupt acknowledge. Then after that, we should also see end of interrupt should be written to both PIC1 and PIC2, and that should be 20, which basically tells the interrupt controller we've finished actually the interrupt. So if we see those things, then we know that the interrupt controllers are pretty much working okay. Okay, so first of all, let's do the test that we did in the previous video. So this is our power on self test and the beep test. So I'm just going to put it in load, send, that's finished. So now what we're going to do is to just check for the logic analyzer. It's hooked up looking at the power on self test port, and I've also changed some of the settings here. We've now actually got the sys buffer chip enable and the DTR as well, and out2 is the output of the timer to the speaker. So if we're getting a beep, then this should actually show here. So I'm just going to run that up. So I've got the post test on the display, just going to press enter. Getting a beep now. Stopped, and then we've got the registers. Okay, so what we can see over on the right hand side here, we've got our power on self test code. So it starts at FF and works its way all the way down to 01. That looks like we're getting our power on self test codes, and if we just drill in at the beginning here, we can see this is where the power on self test codes are going. And then if we drill a little bit further out, we'll see that at some point in time we should get the tones. So this is where we're actually getting the speaker output, and if we look up the top right hand side here, see this is 400 Hertz. So this indicates that our changes with the system buffer and the DTR appears to be working, and we can sort of see here that when we're writing to the timer, then we're also getting the sys buffer and the DTR is looking correct. So I'm going to turn the computer off and back on again, just because we want to do a cold start. We're now going to run up the BIOS. I'm just going to press B for BIOS on the keypad. We should see this start to collect data once we get host codes being written by the BIOS. So just going to press the BIOS now. Okay, so you can see the power on self-test codes here. It started at 7.5 just because that was random data at power on. We can see that we had 01, 02, 03, all the way down to 30. And it isn't continuous, there are the odd sort of jump here. So if we have a look at the error numbers in the BIOS source code, we can see that in fact we've got the initial 01 is start of power on self test, and we can see that we've got the PIC initialization, video BIOS scan, CPU detect, and in fact 30 is start of RAM test. So we've only got 30, it hasn't gone any further, we haven't got any higher ones, but we can see certainly that it is actually going through the initial stages of the BIOS, and we also heard the Intel sort of tune at the power up as well. So that meant that the initial sort of testing of the interval timer was working okay. Now we just need to change the logic analyzer so we can actually look at the system timer, interrupt 0, and also look at the interrupt acknowledge. Okay, so I've put the extra logic analyzer signals on the various interrupt related signals we talked about. I've moved the data connection here off of the power on self-test port on the other side, so it'll only show us the system data bus, so it'll show all the output from the interrupt controllers and also the inputs into the power on self-test. And what I have done in the analyzer for power on self-test, by adding the post chip select on there, we can then filter this on everything beginning with 0x0, and that'll only show us the power on self-test codes. Just going to power on the PC again so that we've got cold start. I'm just going to press B for BIOS. So if we zoom out, just have a look at what's going on here. So what we can see here is IRQ0, the system timer, and if we have a look at the top right hand side here, the frequency, so this is 18.2 Hertz about every 54.93 milliseconds, about every 55 milliseconds. Now, we can also see if we filter over here, the power on self-test codes here, so we can see all these codes. And what we would expect is that until such time as the interrupt controllers have been enabled and initialized, then we wouldn't actually expect to see any activity. You can see that the timer starts to generate interrupts sort of after about 450 milliseconds here, but in fact the first interrupt doesn't actually occur until sometime a bit later. And the reason for that is that it's only when we've done the necessary enabling in the BIOS for the interrupt controllers then we actually see something going on here. So let's dive in and have a look at what's going on. So what we can see here is we have got the IRQ0 as generating the interrupts here, but the first interrupt we actually have, we can see down here, occurring around here. So if we just add some timing markers just so we can find it again. So the interrupt 0 occurs at this time, and very soon after we get an interrupt to the CPU. And what we can see here, this is the interrupt acknowledge. So on the second interrupt acknowledge, then we should expect to see the code from the interrupt controller 08. And if we go to the top here, and if we ignore the fact that we've got the one in front of there because we've got the power on self-test chip select there, then we can see that we've actually got 08 there. So that appears to be working. Although we're not actually seeing subsequent interrupts going further on there. So not seeing subsequent interrupts, we'll just have a look that we do then expect to see that there will be a write to the interrupt controller, and we'd expect to see the end of interrupt to be written to the interrupt controller. So we can see here we've got a write, and if we just look at the value that we've got here, and we can see that in fact 20 is being written to the interrupt controller. So that is the end of interrupt. So it's certainly finished one cycle. So that appears that the wiring is all set up, but we're only getting as far as power on self-test code 30 at the moment, which is start of the RAM test. So there's probably a little bit more we need to look at here. But what we can be pretty sure here is that we have actually got the interrupt controller appears to be working, and we've got the interaction between the CPU and the interrupt controller seems to be working okay here. We've now completed a number of the parts that we need to make a micro IBM PC compatible. We're not going to be bothering with the DMA, and the next major step we need to do is a PC compatible keyboard, and we will also need some sort of video controller as well, so we can see something on the screen. So we've completed the interrupt controllers and our real-time clock. We can't really test the real-time clock until we've actually got something on screen. So in the next video, we're going to be looking at the PS2 keyboard controller, and one of the commenters did suggest perhaps I could try and get the BIOS to send output to the serial port. So I'm going to be looking at that. So the CGA video controller is the next step after the keyboard, but that's going to take quite a while. So if I can get the BIOS writing to the serial port, then we might actually be able to get some information out of the BIOS before we create the video controller. I'm going to break the video there. If you don't want to miss out on future videos, then please hit subscribe, and if you found the content interesting, please hit like. It just helps to make the videos available to more people. Thanks for watching.